Imagine two identical twins, Scott and Mark Kelly. One remains on Earth, the other embarks on a year-long journey aboard the International Space Station. When Scott returns, scientists discover that his cells have aged differently compared to Mark's. This real-life experiment sets the stage for our exploration into how space travel uniquely affects cellular aging. The Kelly twins' story is not just a fascinating anecdote, it's a window into the profound biological changes that astronauts experience beyond our planet. Let's dive into the science behind these changes and what they mean for the future of human space exploration. Microgravity is one of the most dramatic environmental changes astronauts face. In space, the lack of gravity alters how cells behave, leading to changes that closely resemble accelerated aging. Scientists have observed that microgravity can affect the structure and function of cells, from the way they divide to how they repair themselves. These changes are not just theoretical, they have been measured in astronauts like Scott Kelly, whose cellular markers shifted during his time in orbit. Understanding these effects is crucial as we plan for longer missions, such as journeys to Mars or commercial space tourism. One of the most intriguing findings from space missions is the alteration of telomere length in astronauts. Telomeres, the protective caps at the ends of chromosomes, typically shorten as we age. However, during Scott Kelly's time in space, his telomeres actually lengthened, only to return to normal or even short after he came back to Earth. This unexpected result has sparked new questions about how space environments influence cellular aging and what mechanisms might be at play. Could space travel reveal secrets to slowing aging, or does it introduce new risks? Mitochondria, often called the powerhouses of the cell, are also affected by space travel. Research shows that astronauts experience mitochondrial dysfunction, which can lead to fatigue, muscle loss, and other symptoms associated with aging. These changes are thought to be driven by both microgravity and increased exposure to cosmic radiation. By studying these effects, scientists hope to develop strategies to protect mitochondrial health, not only for astronauts but also for people on Earth suffering from age-related diseases. Unlike Earth, space offers little protection from cosmic rays, high-energy particles that can damage DNA and accelerate cellular aging. Astronauts are exposed to much higher levels of radiation, which increases the risk of mutations and long-term health issues. This exposure is a major concern for future missions, especially those venturing beyond the protective shield of Earth's atmosphere. Understanding and mitigating the effects of cosmic radiation is essential for the safety of astronauts and the success of deep space exploration. The DNA of astronauts is under constant assault from cosmic radiation and the stresses of microgravity. Studies have shown increased DNA breaks and mutations during space missions. Fortunately, our cells have repair mechanisms, but these can become overwhelmed or less effective in space. The balance between damage and repair is a key factor in understanding how space travel influences aging and cancer risk. Ongoing research aims to find ways to boost DNA repair for long-duration missions. Space travel triggers heightened inflammatory responses in the body. Astronauts often show increased levels of inflammatory markers, which are also associated with aging and chronic diseases on Earth. This inflammation can affect multiple organs and systems, potentially leading to long-term health consequences. Understanding the triggers and pathways of inflammation in space is vital for developing countermeasures that protect astronaut health and may also benefit patients on Earth. The immune system is another casualty of space travel. Astronauts experience shifts in immune cell populations and function, making them more susceptible to infections and possibly autoimmune reactions. These changes mirror some aspects of immune aging seen in older adults. By studying immune responses in space, researchers hope to uncover new strategies for boosting immunity both in orbit and on Earth. Spaceflight doesn't just affect DNA directly, it also changes the way genes are expressed through epigenetic modifications. These chemical changes can turn genes on or off, influencing everything from metabolism to stress responses. Some of these modifications persist even after astronauts return to Earth, suggesting long-lasting effects. Understanding epigenetics in space could lead to breakthroughs in personalized medicine and aging research. Microgravity leads to rapid muscle atrophy and bone density loss, both of which are hallmarks of aging on Earth. Astronauts must exercise daily to counteract these effects, but some loss is inevitable during long missions. These changes not only impact mobility and strength but also increase the risk of fractures and other injuries. Research into preventing muscle and bone loss in space could have significant benefits for treating age-related conditions on Earth. Space missions disrupt astronauts' natural circadian rhythms due to the absence of a regular day-night cycle. This disruption affects sleep quality, hormone production, and overall health. Poor sleep and hormonal imbalances are also linked to accelerated aging. By studying circadian rhythm changes in space, scientists hope to find ways to improve sleep and health for both astronauts and people on Earth. The psychological stress of space travel is immense. Isolation, confinement, and the constant risk of danger take a toll on mental health. Chronic stress is known to accelerate cellular aging and increase the risk of diseases. NASA and other agencies are developing support systems and interventions to help astronauts cope, which could also inform stress management techniques for people on Earth. To combat the negative effects of space travel, researchers are exploring a variety of countermeasures. These include pharmacological treatments, dietary interventions, and advanced exercise regimens. The goal is to protect cellular health and reduce the risks associated with long-duration missions. Some of these strategies may also benefit people on Earth, particularly those dealing with age-related health issues. Radiation protection is a top priority for future missions. Scientists are developing new shielding materials and exploring pharmaceuticals that can reduce radiation damage. These innovations are critical for the safety of astronauts traveling to Mars or participating in commercial space tourism. The technology developed for space could also improve radiation protection for cancer patients and workers on Earth. The insights gained from studying astronauts have far-reaching implications for health and aging on Earth. For example, understanding how to preserve bone density and muscle mass in space can help improve recovery from hip fractures or osteoporosis. Research into cellular aging in space may also lead to new anti-aging therapies and better management of chronic diseases. Long-duration missions to Mars present unique challenges. The journey exposes astronauts to even higher levels of radiation and more severe microgravity effects. Protective measures must be robust, and countermeasures need to be effective for months or even years. The lessons learned from current space missions are shaping the design of future spacecraft and mission protocols. As commercial space tourism becomes a reality, understanding the health risks of space travel is more important than ever. Even short trips can expose travelers to microgravity and increased radiation. Companies and agencies are working together to establish safety standards and medical guidelines to protect future space tourists. Returning to the Kelly twins, their unique experiment continues to provide valuable data. By comparing their health and cellular markers over time, scientists can isolate the effects of space travel from other factors. This research is helping to refine our understanding of how the human body adapts and sometimes struggles in space. Microgravity is the condition in which people or objects appear to be weightless. In orbit, astronauts experience microgravity, which profoundly affects their bodies at the cellular level. This environment is central to understanding the biological changes observed during space travel. Telomeres are repetitive DNA sequences at the ends of chromosomes that protect them from damage. Their length is considered a marker of cellular aging. Changes in telomere length during space missions have provided surprising insights into how space environments affect aging processes. The study of cellular aging in space is just beginning. As we prepare for longer missions and commercial space travel, the knowledge gained from astronauts like the Kelly twins will be invaluable. These discoveries not only help protect space travelers but also offer hope for new treatments and healthier aging on Earth. The journey to understand how space affects our cells is far from over, and the next chapter promises even more exciting breakthroughs.